Oh, welcome back to our final lesson for this chapter. We're going to do one more inference procedure, and this is with slope. We're going to do some hypothesis testing for slope. So our goal for today is to be able to conduct a t-test for a slope. Now, if you don't already have this down in your notes or in your graphical organizer, these are things that we've done to this point. We need to understand all the required conditions before doing an inference procedure. That's at the top here. And last time we talked about confidence intervals, where we did a t-interval for slope. We identify what the parameter is. We check the conditions. We use the formula to state the degrees of freedom. We find the actual interval, and notes over to the right where degrees of freedom is n minus 2. S sub b is also called SE sub b. That is the standard error of the slope. B is the slope from the least square regression line. From our sample data. It's important to explain the confidence interval in terms of slope for each additional blank. Y increases or decreases by that, so we understand the full context. Now today we're going to get into the hypothesis tests. Okay, so here's an example we want to look at. Do customers who stay longer at buffets give larger tips? Now we've actually already looked at the same exact data, and we checked all the conditions. We were just trying to see if there's a relationship between the amount of time they're staying at the buffet and the tips they leave. So we actually did some regression analysis, found a least square regression line, and we checked conditions. The question is, do the data provide convincing evidence at the 0.05 alpha level of a linear relationship between the amount of time and the amount of tip for customers at this Asian buffet? Okay. Now, one thing I want to note is whoops, right here. Do the data provide convincing evidence of a linear relationship? That should indicate to us that we are doing a test, a hypothesis test. Okay, we have an alpha level of 0.05. We want to end up finding a p-value. So let's think back to all the hypothesis tests that we've done to this point. Okay, what do we do first? Well, of course, we state the parameter, and this is going to be slope. So beta is the true slope of the line relating time and tip, so time in minutes, tip in dollars, for buffet customers, we'll say. And with every hypothesis test, we need to state hypotheses. So this is where it's a little bit different. So our null hypothesis is typically going to be that there is no linear relationship. So the true slope is 0. 0 is no slope. Okay? So I'm just going to make a note, no linear relationship. Whereas our alternative in this case is going to be that beta is not equal to 0, meaning there is a linear relationship. Now it might be specifically asking if there's a positive or a negative, and that would be a greater than or a less than symbol instead of a not equal to. But in this case, we're just looking for a linear relationship. Now we want to go into the conditions. And we've already checked these. We went through all of these in a previous lesson. So I'm going to say checked and met in previous lesson. Nice. Conditions are done. Boom. Let's get into the actual test. Okay? So this is going to be called a t-test for slope. And we need to find a t-value. Okay? So that's where I want to take you to this. Now, if we go back to our formula sheet, after checking conditions, we can perform inference with slope. Conducting a hypothesis test, our general test statistic, in this case it's t, is going to be your statistic minus your parameter divided by the standard deviation of that statistic, or standard error. So in this case, what goes in there? The statistic would be our little b, whatever we get from our sample data, minus beta. Now, beta is going to be coming from our um, our hypotheses. So usually 0. I can't think of an example right now where it wouldn't be 0. It's going to be usually 0. It's from our null hypothesis. Okay, so reminder of that. And then divided by the standard deviation, that's S sub B. Okay, now all this information we can get a couple different places. So B minus the hypothesized slope over the standard error of the slope, that's another way to write it. Degrees of freedom is still going to be n minus 2. Now before we look at actually getting that information, it may be worth writing down in your formula, or in your notes, or on your graphic organizer, the rest of this. So I'm going to leave this here for a second, and just note a couple things, and then we'll go back and finish up that t-test. Now this is a t-test for slope. That's the name of it. The conditions are going to be met above. That's using the acronym LINER again. Hypotheses, we have to state our parameter first, but then our hypotheses again, our alternative is either going to be not equal to, greater than, or less than, and I have those three things listed here. And we've got the formula we just talked about with degrees of freedom. And the key points I really just want to make note of when you're given a computer printout, and we'll see the one with our second example here in a little bit. But everything there that we've done to this point, we've talked about. We're adding a couple more now, and that's in these boxes here that actually are useful for a t-test. We get a t-value, that's our test statistic, and a p-value. All right? This is a p-value for a two-sided test. So if you're doing a one-sided test, you'd have to divide that by 2. I want to make a big note of that. But that is so nice if it actually gives you all that information. Okay? So let's go back, though, to our example and finish this up. So for this one, generally it's going to be b minus beta over s sub b. And where are we going to get that stuff from? We're going to have to use our calculator function. Now, the other nice thing is we have calculator features that will do that for us. So I'm just going to show you that little printout of those. So last time we ended up doing linreg t interval. Now we can do linreg t test. So if you go to stat tests, for me it's F, and when you pull that up, it'll look like this. We're going to use list 1 and list 2. We have to have that data in list 1 and list 2. The only thing you really have to change, so we're going to leave this again as 1. The only thing that you have to know to change is a less than, a greater than, or a not equal to for our alternative hypothesis. Now, we are doing this. Theoretically, if we were going to do a test for correlation, the R value, I'll make note of this. We're not going to ever do that, but this thing right here, it's like, it looks like this. This is rho. It's the true correlation. We're not ever going to deal with that in this class. Correlation. Sorry, I totally butchered that one. But in case you see, we're not going to actually use that at all. We're just dealing with slope. And then you can calculate it. So when you calculate it, it'll give you the information you need. I have it here for you. It ends up being 1.231. That's what I got. Now, I want to state the degrees of freedom, n minus 1. My n, we had how many? $12 of them. So it's 12 minus 2. 10 degrees of freedom. The nice thing is, if you use your computer printout, You don't actually have to go to your table or use TCDF. But if you didn't have that information, you'd have to do that. But it would give you your p-value is 0.2466. So we can now draw our conclusion that because 0.2466 is greater than 0.05, or really any logical, reasonable alpha value, we would have to fail to reject the null. Okay, we don't have information, or we don't have convincing evidence that there is a linear relationship between time and tip at a buffet. So this is important. Like, if we want to know if there's actually a linear relationship, this is a good way to test that out. You can utilize a t-test for slope to see, is there evidence that there actually is a linear relationship? Because otherwise, even though it might look like it is, maybe there's not enough evidence that there actually is. Okay? And this is just based on what we have. So I want to glance at one additional example, a little bit different in what's given. But I want you to look at this first. So, and check out the conditions first. So it says infants who cry easily may be more easily stimulated than others. So infants who cry easily may be more easily stimulated. This may be a sign of higher IQ. Child development researchers explored the relationship between crying in infants 4 to 10 days old and their later IQ test scores. A snap of a rubber band on the sole of a foot caused the infants to cry. That seems like it's wrong to do that, but they did that. They recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds of the crying. Later, they measured the child's IQ score at age 3 using the Stanford Binet IQ test. Using data from a random sample of 38 infants, a computer output from a least square regression was run. Can you please check the conditions? Ready to go. Now, at this point, hopefully you were able to check the conditions and actually see that they theoretically were all met. Not everything's perfect, but it was enough to say that, yeah, I think those are met. So let's answer the question. Do these data provide convincing evidence at the 0.05 alpha level of a positive linear relationship between the count of crying peaks and the IQ in the population of infants? I'm giving you a computer printout. You still have to go through the different parts of a hypothesis test to do this, but you can use the information given in this computer printout. So make sure that first you identify your beta. It's the true slope of the line relating we'll say cry count, or the number of crying peaks, and IQ at age 3. Okay? Now, gotta check your conditions. And if you checked them properly, I'm going to make note that they were met and verified. And I'm going to move on. We need our hypotheses. So The null hypothesis is always going to be that there is no linear relationship. So beta is equal to 0. No linear relationship. The alternative in this case is looking for a positive, so it's greater than 0. So note that it's a positive linear relationship, so that's why we're going to use greater than or equal to 0. So that's the case where you have a one-sided hypothesis test. Okay? Now, we want to run our test, and this is going to be a t-test for slope. And what do we need? We need a t-value, we need a p-value, we need our degrees of freedom. We don't even have to list the work for it. And guess what? We have most of that stuff. We have a t-value. We have a p-value for a one-sided, or for a two-sided test. We're working with a one-sided test. It doesn't give us our degrees of freedom, but we can figure that out based off of the number of data points we had. Okay, so I want to go back. There was 38 infants. Okay. Whoa. Switch that back. There we go. So our t-value is at 3.07. Boom. We got our t-value. Our degrees of freedom, 38 minus 2 is 36. Got our degrees of freedom. Our p-value is not 0.004. It's that divided by 2, so it's 0.002. Either way, it's a very small p-value, which tells me that we can reject the null hypothesis. So, because 0.002 is less than 0.05, we can reject the null hypothesis. There is convincing evidence of a positive linear relationship. Between these crying count peaks. And IQ at age 3. Boom. So, valuable information comes from a computer printout that makes our life way easier when we're doing these tests. But that's really the two kind of things that you'd be seeing when you're dealing with a hypothesis test for slope. And that's section 12.3D. We'll see you next time.